Hi everyone. Uh, in the last 2 months, I've been receiving a lot of emails and messages on LinkedIn, especially from students from BITS Pilani, asking to give a roadmap of this course on microelectronic circuits because they say that I've uploaded nearly 80 lectures. And because usually what happens at BITS, I'm assuming that's the case with most other institutes as well. We have this mid-semester exams, and if a student doesn't perform very well, it's very common for them to try and catch up in the end semester exam. So they would normally start preparing after the mid-semester exams. Okay, so I think that's why I've been receiving a barrage of emails. Unfortunately, I couldn't reply to all of them. On top of that, in case some students may want to revise the subject during the summer vacations as well, because if you are studying the subject during summer vacations, you are studying it without any pressure on you. You are just studying purely for the love of the subject. And also next semester, they have a course in at the institute where I used to teach. We have a course called Analog and Digital VLSI Design. We famously call it ADVD. It's a course that it's a follow-up course to microelectronic circuits, where we go into the design of op-amps. So the students have been asking me to give a roadmap as to how to prepare for this course, microelectronic circuits. I know it's a little late. The end semester exams or the final exams at BITS have already started. I'm aware of that. So, but anyways, I just found some time now. I thought I'll make this video, and it will be useful for students who want to, let's say, prepare during the summer, or maybe next year for the next batch of students as well. Yeah. So one of the common questions when I teach undergraduate courses that I normally receive from students is that they want to understand why are they doing a certain course. Okay, they entered the undergraduate program. A lot of times, majority of the class may not be as passionate about the subject, so they just take the course because in India we have this allotment of different degrees based on their scores that they score in their entrance exams. And so students are usually, if you want to get students interested in a subject, the first thing they want to know is why are they doing this course, and what impact does this course have in the practical, in the real world. Okay, so that's something usually in any undergraduate course, that's what students will look for. In a master's course, students more or less are aware of why they are doing a course, so they want to look for more details. So I've made nearly 80 lectures on microelectronic circuits. So this was made in almost, it's been like 4 years now. And when I was teaching before, almost 4.5 years since I uploaded those videos on this course. And these 80 lectures, my intention was to give especially students who already were attending my classes, and then so that they can use those lectures while preparing for exams and all that. Okay, or campus placements and all that. So if you're directly going to start off watching those videos, I don't give the motivation as to why you want to, why do you have to, learn the subject. I don't give that motivation. Usually I used to have one lecture just before I begin the course to, draw the attention of the student. So I used to give them history of this subject, and also maybe motivation as to why you're supposed to do this course. So because I didn't upload that video, I thought I'll make this as an introductory video, and also a roadmap on how you can prepare for this course on microelectronic circuits. For students from other institutes, this is a basic and introductory course on VLSI design or analog IC design. After that, in the next semester, we have a follow-up course where we teach, where we go in greater depths about the design of analog circuits like operational amplifiers and band gap references and so on. Okay, now back to this course. So if you see, we are now living in an age of electronics, right? So every human being carries an electronic device with them. So which is your cell phone. Some of you might be wearing AirPods. You may be even sometimes a lot of students carry on their backpacks, they would be carrying tablets and laptops. So almost every human today carries an electronic device, whether it's a laptop or your cellular phones, or any Bluetooth devices like your earphones and all that. And almost all of these devices, whether it's a laptop or a cell phone or a computer or desktop computer, or any appliance in your household, or let's say you're watching some television. You would be hearing the audio through an audio amplifier or a speaker, or you may be speaking to on a microphone, and then that will further be heard through a speaker. So almost all these circuits, all these electronic circuits, do one very simple mathematical operation. Okay, they do a range of mathematical operations. If we use all of these electronic circuits, at its heart, all these circuits, they are performing some very simple mathematical operations. And among these operations, there is one specific mathematical operation which is central to all of analog circuit design. And that mathematical operation is amplification. What is amplification? Let X be an input. Okay, X is assume, for example, X can be a time varying signal. So what is a time varying signal? So for example, what I'm speaking right now, let's assume I say I'm going to start now. From now onwards, what I speak counts. So that becomes your 0 time instant. From now onwards, if you pass what I'm speaking through a microphone, the output of a microphone will be, a microphone is a device which can convert voice signals to electrical signals. So you will generate a voltage signal which will be varying with the time. Okay, so this is what we call as a signal. Since you guys have done a basic course on signals and systems, you know what is a signal. Okay, I'm giving an example. What I'm speaking now is a speech signal. You may be watching a video, that's a video signal. Okay, so if you have this a signal, let's call it X. An amplifier is a device which will take this signal as an input and produce an output Y, which is simply an amplified version of the input. It's just mathematically just a scaling operation. You're just taking the signal, multiplying by some factor, and that's your output. And if you see, right, if you think about it, now that I've been in this field for nearly 20 years, if I count from my undergraduate days, almost every analog circuit that I've designed or worked with or taught, in some way or the other, performs this very simple amplification operation. Okay, it just performs this very simple scaling operation. It takes an input signal, multiplies it. So if you, for example, let's say we talk about your cell phone. A cell phone is constantly performing this operation. Where does it perform? When you are browsing on your cell phone. Okay, what does your cell phone do? It talks to a nearby Wi-Fi router. It talks to a nearby base station tower. So you have electromagnetic signals, electromagnetic waves, which will travel from this base station tower or from your Wi-Fi router into your cell phone. These signals are very weak. Okay, these are electromagnetic signals, and again there is a device called an antenna which converts these electromagnetic signals to electrical signals. Okay, then you can perform amplification operation and all that using some circuits. So your cell phone is constantly receiving signals from these devices, wireless devices. It can even be connected to a Bluetooth device. So when it is connected, when it is interacting with these devices, you have I'm going to use the word information or electromagnetic waves flowing from these devices or base station or routers to your cell phones. And these signals will normally be very weak. So the first operation, your cell phone circuits, when the signal enters the cell phone through an antenna. So this is a symbol for an antenna. If your signal enters through an antenna into your cell phone, the first operation your cell phone performs is amplification. It's called low noise amplification. You don't have to worry about that. The operation it performs is amplification. It just boosts the input signal, and once the signal is boosted, then we do some other mathematical operations. So if you see, almost every device, if you take a microphone, immediately if I'm what I'm talking right now, right, I'm speaking into the speaker, into the microphone of my tablet. Internally there is an amplifier which will amplify the signal at the output of a microphone. Okay, usually the output of a microphone will be very weak, very small voltage signals, which needs amplification. Similarly, when you are hearing this, for example, let's say you are playing a YouTube video and you are hearing this, that audio signal comes out of speakers. Before the speakers, again, there are circuits called as driver amplifiers, or these circuits which will drive these audio speakers. Okay, so again you will be performing this mathematical operation, which is why I said it's a very fundamental operation. When you think of it, almost every device that you guys are using right now performs this very simple operation called amplification. Amplification is nothing but you take a signal, multiply it by a factor. Okay, so that's a very fundamental operation. And if you see, this entire course, microelectronic circuits, just teaches you how to build these amplifiers. It's just a simple operation. All the circuits, what you'll be learning in this entire course, all the circuits will perform this very simple operation. You feed an input signal, it's just going to amplify it and produce an amplified version. This amplification factor can range from 1 to, depending on the circuit, depending on the application it's being used, it can go as high as 10 power 3, which is normally we express gain in decibel units. You will see how to express that in this course. Or it can be in several orders of magnitude, 10 power 3, 10 power 3 or 10 power 6. You will learn such high gain amplifiers in the next semester's course, which is ADVD. Okay, at that time you'll be building circuits called operational amplifiers, where you can actually you do normally build circuits with gain as high as 10 power 6. Okay, so how do you build all those circuits? We lay those foundations in this course. Okay, so the simplest operation is just one thing that you will be learning throughout this course, how to do this amplification. But the thing is, to do this amplification is a very tough task. You have to do this amplification under different conditions. It's very challenging to realize this operation faithfully, perfectly. So how do you build an amplifier? That's all this entire course is about. Okay, this especially, I also give normally a comparison between the course on microelectronic circuits to computer programming, because most of you have done a basic course on programming. So when you are doing programming, so what is the purpose? What purpose does a program serve? So usually you will have some application. You want your computer to do a certain operation, then you write a program. And program, you can write a program in different languages, and each language contains its own set of syntaxes. So this course, you can think about what you're learning in this course like as though you're learning syntaxes. You're learning the building blocks necessary to write a complex program. Okay, so you're learning the building blocks and all the different ideas which are necessary to build more complex circuits in the next semester, which is you'll be doing a course called ADVD. That's where this will be very useful. Okay, so that's the motivation. So this entire course is just to perform this simple operation, y equals ax. How do I perform amplification? What are the different ways in which I can perform amplification? Mostly we focus on MOSFETs in this course. And if you have just taken any basic course, because you have already done electrical sciences, you know that you can use transistors to build amplifiers. So, and we have been building these amplifiers for almost 100 years now. Okay, more than 100 years, little more than 100 years. So the first amplifiers were built using devices called vacuum tubes. This was in 1910, late 19, just around 1910. We were building the first amplifiers using vacuum tubes. And then we switched to bipolar junction transistors, 1940s and 50s. Then MOSFET was invented in 1960. It's an old idea, but the device was actually fabricated and invented in 1960. And after that, we started building amplifiers mainly we were building using BJTs, but slowly MOSFET has its own advantages. And then with the explosion of digital technology, we started building circuits using MOSFETs. So mainly this course, we will focus on MOSFET based circuits. We will not be teaching much about BJTs. In fact, when I was studying, bipolar junction transistors were taught extensively. And then they used to teach us MOSFET based circuits, because when I was studying as a student, more or less MOSFETs had by then phased out bipolar junction transistors. But still bipolar junction transistors were still used in some applications, so they used to teach us. And if you look at the commercial op-amp ICs, which is called 741 and all that, you will be using these operational amplifier ICs in another course, which I was involved in the lab of that course. You'll be building another complex integrated circuits into ICs or chips, analog chips, which you'll be encountering in a different course. And those amplifiers are all built using bipolar junction transistors, which is why they used to teach us BJTs as well. And when I was teaching the course, I normally give some idea about BJTs, but mainly the focus will be on MOSFETs. So that's the whole idea behind the course. Why are you learning? Just to understand this mathematical operation called amplification. How do I do this amplification? And I'm telling you, that's the single most fundamental mathematical operation that every electronic device that you guys use performs. From cell phones to laptops to tablets, and most of your electronic appliances, which probably are talking to wireless devices, all of them performs this very simple operation. And that is why when you are designing this course is actually an introduction to integrated circuit design. Okay, but we start off with teaching amplification because that's the most fundamental operation. Okay, so now I'll come back to the prerequisites. What do you know? What should you know before you start studying this course, before you start taking this course? So the students at BITS, you guys do a course called Electrical Sciences in your first year, which is a course where we teach you basics of Kirchhoff's current laws, Kirchhoff's voltage laws, mesh analysis, nodal analysis. So you should know the basics of how to do all this. If not, you can spend 5 to 6 hours watching any videos you like, some basics on how to do KCLs and KVLs. If you're starting from ground zero, I'm assuming, say you're just beginning to take up this course, and because you have taken this course on electrical sciences 1 year ago before you take up this course, so you might have forgotten it. So just some quick revision would be very helpful if you're going to take this course. Okay, then the other most important thing is understanding independent and dependent voltage sources and current sources. What is a current source? What is a voltage source? You should have a good understanding of it. So I normally teach that in 1 hour in this course on microelectronic circuits. But if you guys are interested, you can watch just study about independent and dependent voltage sources. What do they mean? What are the IV characteristics of independent and dependent voltage sources? What do you mean by IV characteristics? Go through that. So I have my playlist called Electrical Sciences, it's called Electrical Sciences Passive Devices. You can go through that. Okay, the initial 4-5 lectures will tell you that. Then you have to know basics of passive circuit elements like resistors, capacitors, and inductors. Mainly inductors are not very useful in this course called microelectronic circuits. Mainly we focus on resistors and capacitors. So you should know you should know the functionality of resistors and capacitors. And I would again recommend that I have a playlist on electrical sciences. I spend some time teaching how resistors behave, how capacitors behave. 4-5 lectures. Initially I uploaded some lot of videos on passive devices, but you can pick initially some 8 or 10 videos on resistors and capacitors. Okay, it will totally come to 5 to 6 hours of content. In case if you are interested, you can watch it. Okay, you should know that because it's a prerequisite, and you should watch it definitely if you are interested in going into this field, or if you are preparing for placements and all that. You should watch that. Then the standard, the usual stuff, which is Thevenin and Norton equivalents. You should know this again because we will be using this when you're analyzing some circuits in this course. So you should again know this as well. Okay, Thevenin and Norton equivalents. So these are the prerequisites. Again, you can watch some YouTube videos on how to do the Thevenin and Norton equivalents. Before you take up this course, we expect that you are aware of all this stuff. Okay, so the next thing is what we call biasing. So this amplifiers, we build amplifiers using transistors, which happens to be BJTs or MOSFETs. If you want to use these devices as amplifiers, we have to do something called biasing. Okay, biasing is setting up the device so that the device is ready for amplification. Okay, so one example I remember, since this is an undergraduate course, one of my professors used to tell us this example. This was long time back, and I remember the professor telling me that he read that example in a book. What he would normally refer to was the pull-up bar. So if let's say you want to do pull-ups, let's say you have a human of a certain height, you want to do pull-ups. The pull-up bar cannot be too close to the ground because you will not be able to do pull-ups using that bar. It cannot be too far away from you as well. It cannot be placed at a much taller height than yours. Again, you will not be able to perform pull-ups. It should be at a nominal height where you can reach the pull-up bar using your hands. So this operation of placing the pull-up bar at the right position so that you will be able to do pull-ups can be seen like an amplification biasing operation. So you have to bias you have to ensure that the gate to source voltages or the drain to source voltages are all proper, and and a certain drain current is flowing in a MOSFET. Then you apply small signals, then it can act like an amplifier. So this act of setting the right voltages, gate to source voltages and drain to source voltages, is called biasing. So again, this is something we teach in a course called Electrical Sciences. You should know how to do biasing of amplifiers. So usually what happens in biasing is you set the MOSFETs to have a fixed VGS and drain currents. Okay, so you set the MOSFET, you size the MOSFET's sizes such that it's able to carry a given drain current for a given gate to source voltage. How do you do that? There are different ways of biasing. Any course in the course on microelectronic circuits, I do go through the basics, but I assume that you know this. Okay, so you can go through your electrical sciences lecture notes or any this biasing. These are all very old concepts. You can just Google search biasing, or I would recommend that you start using the generative AI models. You can just ask them, what is biasing? Can you give me some examples of biasing? Suggest me some textbooks. You can ask all of that and learn by step. There are different ways in which you can bias MOSFET amplifiers. A simple biasing, resistive divider based biasing, using DC voltage source to bias. Okay, so there are different ways of biasing the MOSFET amplifiers. You should know how to bias it, and how do you set the device dimensions and set the current, set the proper DC operating conditions. When I say DC operating conditions, I mean the correct VGS, the right drain current, the right drain to source voltage. All these has to be in the right, they have to be properly ensured that these voltages meet certain conditions. Only then your MOSFET will act like an amplifier. So what are these conditions? These conditions are called saturation region and all that. So that we discuss in the course. I don't go very deep into this in this course because I assume that you are already aware of it. So you can watch any lectures on basics of electrical sciences to understand biasing, amplifier biasing. So once you understood now by the end of this biasing, now you have understood, you are comfortable analyzing circuits. You have understood what biasing is, and then you are comfortable analyzing MOSFET based circuits. You are comfortable analyzing circuits which contains dependent, independent sources, resistors and capacitors. Now you have to go to what we call small signal models for amplifiers. Again, this is something we assume you know that. This course we give a very basic idea, and then but we assume that you at least know some basics of small signal models and how to do small signal analysis of amplifiers. So once you have a DC biasing circuit, then you'll apply a small signal AC signal to a circuit. Once you apply a small signal AC to the circuit, you should be able to draw an AC equivalent model. What is an AC equivalent model of a circuit? Then from the AC equivalent model, you should be able to draw and understand small signal models. So I have taken a very simple circuit here. This is called common source amplifier. You have a MOSFET whose drain is connected to a resistor to the supply. So if I have to draw the small signal model, you will represent it using a simple linear circuit model for this MOSFET, so that it will act like an amplifier. Okay, so how to do the analysis, all that I discuss in that course on microelectronic circuits. Again, this is something we expect you to know a little bit, so that it will be very helpful when I'm teaching this course if you're already gone through that. So usually we spend the first 2 weeks covering all these basics so that you get into the groove of this course. Then we start into the actual content for the course. So until now, what we have discussed is basics of circuit theory, biasing, small signal models, analyzing amplifiers using small signal models. All this is considered as basics for this course. From now on, we start going into the actual course. We will teach you, as I said, this course, we teach you the syntaxes required to learn this language. So we will teach you all the basic building block of an amplifiers. What are the different kinds of amplifiers that are commonly used? You can take a MOSFET and build amplifier out of it, and there are different ways in which you can build amplifier using MOSFETs. They're called common source amplifiers, common gate amplifiers, common drain amplifiers, cascode amplifiers and cascade amplifiers. So we discuss all these amplifiers, and whenever for all these different amplifier topologies, you should know how to bias the amplifier. Once you know how to bias it, then you should be able to find the small signal voltage gain. And once you know the gain, you should be able to find input and output impedances. Usually these things matter when you're actually building any practical amplifier circuits. These things matter. Input and output impedances also matter, and we give the reasoning for why it matters in the course. And since we are teaching so many topologies, what can you do? What kind of an amplification you can perform using each of these amplifier topologies? And what are the advantages and disadvantages of each of these topologies? Okay, that's what we cover in the course in great detail. So which is also something that I've discussed. But if you know what to study, if your basics are strong enough by this point, you will be very easily be able to follow what I've uploaded on all these different amplifier stages. Okay, see, once your basics are strong, right, you'll be able to follow what I'm trying to say there. If you directly go and watch it, because I don't give an introduction, I'll directly jump into the technical content of the course. So some students wrote to me saying it's, they want the motivation for the course, which is why I'm making this video. So this course, we teach you amplifier topology. This is where the course starts. We teach different amplifier configurations, how to analyze all these amplifiers and different kinds of amplifiers. We also talk about advantages and disadvantages of these amplifiers. Once that is done, we teach another very important concept called differential amplifiers. Okay, so these differential amplifiers have certain advantages. It is just a regular amplifier, but we will be using two such amplifiers instead of a single amplifier, and they offer some benefits, okay, compared to a regular amplifier. So what do you mean by differential amplifiers? All that you will learn in the course. How to analyze these differential amplifiers, how to do small signal analysis, how to do basic circuit analysis of differential amplifiers. So there is something called common mode and differential half circuits. So all this falls under the category of analyzing differential amplifiers. Okay, then you'll have to find common mode gain and differential mode gain. So you will understand what do these terms mean if you go through these lectures. I think this part I've covered pretty decently. How to draw common mode and differential mode circuits, and how to analyze these circuits I've spoken in good detail. Okay, so you can watch that. So once we are done with this, at this point, we have given you more or less all the syntaxes, meaning you know what are the different amplifiers, and also we spoke about what are differential amplifiers, which are more popular circuits as well. And once you know this part, you are now equipped, or now you have understood more or less what kind of amplifiers, what this course is about. Okay, and usually this much we cover for your mid-semester exams. Okay, this is what we cover. We single stage amplifier topologies and differential amplifiers. Once you are done with this, the next thing we talk about is what we call the frequency response of amplifiers. So when you build when I said amplifier is just what? You get an input signal X, your output of this amplifier is supposed to be A times X. Okay, it's a scaled multiplication of the input signal. Now what happens is when you build these practical amplifiers, the amplification factor, the gain here, will depend upon the frequency of the input signal. So if I apply an x of t is assuming is an input sinusoid. See, generally again, why do we take sinusoids? Because you must have studied by now in a course called Signals and Systems that most signals can be broken down as a linear combination of sinusoids. That follows from Fourier transform, Fourier series, and Fourier transform analysis. So if you understood how the circuit behaves for sinusoids, then you have more or less understood how the circuits can behave for most of the practical input signals. Because most of the practical input signals are linear combination of sinusoids. So understand how the circuit behaves for sinusoids of different frequencies, then you have understood how the circuit will behave for any input signal. So now what happens is we feed the sinusoid and vary the frequency. And we will find out when you analyze the circuits that this gain depends upon frequency. So this behavior, this study of these amplifiers, the amplifier's gain as a function of the input signal's frequency is called frequency response. And we spend considerable amount of time introducing the concept of frequency response. So here we assume you know some signals and systems concepts as well. We know what Laplace transforms are. Okay, and another important thing here, we teach Bode plots. What are Bode plots or Bode plots? How to draw a Bode plot for an amplifier. Okay, Then we introduce the concept of poles, zeros, and frequency response. So what is frequency response, what is a pole, and what is a zero? We introduce all these ideas in this part of the course. Once we are done with the basics, this is the mathematics of this course. I think I usually spend a lecture or two on this. But if you have done this as a part of this course on control systems or signals and systems, you are good to go. Okay, you understand all this. So you know why are you studying this. Okay, why are you studying this? Because you just need this very simple mathematical operation, y equals a times x. But it turns out the gain here depends upon the frequency of the input signal. So then I'm interested in knowing what we call the frequency response, which is nothing but gain as a function of the input signal's frequency. Okay, that's a very useful graph. So then you will know when to use, for what frequency range you can use this amplifier for. Okay, so that's why we study frequency response. So we take the frequency response of all the amplifiers, what we have discussed so far, the common gate, the common drain, the common source, all these amplifiers, cascade, and the differential amplifiers. We perform a very in-depth frequency response analysis of all these circuits. So by the frequency response, you will know which amplifier will amplify for a wider range of frequencies. Okay, we introduce a term called bandwidth, and we say circuits which can amplify signals over a wider range of frequencies. We'll say such circuits have wider bandwidth. Okay, it's a very useful concept when you're learning, how to build amplifiers. This is again a very important concept that you should be aware of. The frequency response of amplifiers. Okay, how does the gain change as a function of frequency? So usually what happens is most of these amplifiers will be driving capacitive, will have something called capacitive loads, and because of these capacitors, the impedance of a capacitor decreases with increasing frequency. So your gain will also have some dependence on the impedance of a capacitance, and it will start decreasing with increasing frequency. Okay, so that you will study for different amplifier topologies in great detail. Okay, why are you studying this? Because it turns out the gain is a function of frequency, and that's why I need to study this. And finally, we end the course, because it's a single semester course. We can't be teaching a lot more ideas. So we end this course by teaching you a very, very important concept in electronic circuits or electrical and electronic circuits called feedback. Okay, normally what feedback is, you are building an amplifier normally. We take a part of the output and feed it back at the input. You do some simple mathematical operations at the input, and this gives you a lot of advantages. So feedback again is a concept as an idea. It was developed again more clearly close to 100 years ago, but it's been one of the most commonly used idea in circuit design. So we teach you guys what is feedback, what is negative feedback, why is it used. Generally I give a history. When the first engineer who was building circuits, how did he come up with the idea of negative feedback? So I go through some history, and then we talk about what is feedback, open loop gain. You will understand what do these terms mean once you go to that part of the course. And closed loop gain. Again, we'll study, see, anytime you talk about amplifiers, what are the things we are interested in? We are interested in the gain of the amplifier. We are interested in the input impedance, input and output impedances. So we study what happens when you add feedback. Okay, what happens to the closed loop or the feedback circuit, the gain, input and output impedances of this feedback circuit, and what does it depend upon. We study all of that. Okay, then we teach you guys how to analyze circuits with feedback. Once you have, the circuit becomes complex. So how do we analyze the frequency response, or how do you analyze such circuits? So we actually teach you how to break the loop. Anytime you have a feedback, you're feeding the signal back, so the circuit forms a loop, and we have to analyze the circuit. We usually break the circuit at some point and teach you techniques on how to analyze all these circuits. Okay, so then how gain changes, what are the advantages and disadvantages of feedback, all those concepts are discussed in this part of the course. Usually we end this course at this point. If we have time, we go for noise. Okay, we teach you noise in this semester itself, but generally we don't get time. By the time we finish this, we have done more or less, we have spent a lot of time, and so we usually stop with this course. The next semester's course, which is called ADVD, right now I'll probably make a video for that some other day. We teach you what is voltage noise. Then we teach you how to build a set of circuits called operational amplifiers, which will also involve negative feedback and all that. So that will be like we spend usually 20 lectures on that, and then we say we close that part of the course. Okay, then we go to digital IC design. So that's it. So that's all about this course on microelectronic circuits. Hopefully this was helpful. In case you guys have any doubts, you can write to me. I'll definitely get back when I find time. Okay, thank you.